Hi everyone, my name is Kaylin and today I'd like to talk about hydrogels for multifunctional energy therapeutic platforms. Think about the last time you scraped your knee. Maybe you put a bandage on it and it healed. But for deep chronic wounds, traditional dressings are essentially useless. For this reason, hydrogel technologies are widely valued for their likeness to biological tissue. But they face a persistent mechanical to functional trade-off. Traditional hydrogels often face two main problems: structural fragility and poor fatigue resistance due to their single network architecture. They are also non-functional, so the objective of this research is to move beyond stimuli-responsive gels with the help of two emerging materials, which are phase transition hydrogels and phase change hydrogels. The difference between these two lies in their thermodynamic driving force. For PTHs, they are entropy driven, meaning that they rely on the balance of polymer to solvent interactions. For instance, poly-N-isopropyl acrylamide, or PNIPAM, it exhibits a lower critical solution temperature of around 32 degrees C. Below this temperature, the dominant intermolecular forces are hydrogen bonds between the polymer chains and water. So this keeps the gel swollen. And above the LCST, hydrophobic interactions between the polymer backbones take over, causing a collapse and the ejection of water. PCHs, on the other hand, are enthalpy driven. They incorporate phase change materials such as polyethylene glycol or hydrated salts. These systems store and release energy via latent heat during solid to liquid or amorphous to crystalline transitions. The performance of these materials is also highly dependent on their network architecture. Two critical parameters are mesh size, which is the physical distance between the crosslinks, and network density. In PTHs, a larger mesh size facilitates higher water uptake and faster diffusion, which is essential for rapid volume changes. So back to the problem mentioned in the start, how can the structure stability be improved? To overcome the fragility of pure hydrogels, structural stability is enhanced by combining two types of networks, which are permanent covalent crosslinks and reversible physical crosslinks, such as hydrogen or ionic bonds. These dynamics reversible bonds act as sacrificial elements that break down and reform, allowing the material to maintain structural integrity during repeated cycles of swelling and deswelling or phase transitions. Furthermore, rheological behavior can be optimized by integrating inorganic nanoparticles. These act as a secondary cross-linking sites. When stress is applied to the tissue, these nanoparticles dissipate the mechanical energy and enhance elasticity, toughness, and durability. Also, by tuning the molecular weight and network density, the gel solubility can be programmed. This is key because it allows the scaffold to exist as an injectable sol that flows into a wound, only to transition to a high viscosity gel that perfectly matches the tissue's morphology depending on the tissue's temperature or pH. And this is achieved by the covalent and reversible physical bonds. That's why having a dual cross-linking network is essential. Beyond reinforcement, these particles act as stimulus transducers. For example, metallic nanoparticles such as gold nanorods allow for photothermal conversion. So when temperature is applied, these hydrogels can help cells trigger biological functions to promote healing. Another example is iron oxide, which acts in the same way by responding to magnetic field. So in conclusion, phase transition and phase change hydrogels represent a paradigm shift, bridging polymer chemistry and functional engineering. While challenges like long-term stability persist, recent breakthroughs in nanomaterial reinforcement and bio-inspired designs are rapidly overcoming these hurdles. These smart materials, which are defined by their stimuli-responsive, biocompatible, and self-healing properties, are moving beyond the lab. With their versatility in different applications, PTHs and PCHs are poised for commercialization as sustainable multifunctional platforms for the next generation of adaptive technology. So Thanks for everyone's attention, and that will be all from my part.